So in this video, we're going to be looking at another type of chemical reaction. In the last video, you looked at single replacement reactions. In this video, we're going to be looking at what is called a double replacement reaction. So in double replacement reactions, the ions in two different compounds are going to change partners. What that means is that the ions are going to basically switch and create two new compounds. So if our first compound was this idea of A and B, and the second compound is C and D, then they're going to just switch who they're bonded to. So A is going to end up being bonded to D, and C and B are going to end up being bonded to each other. And remember here, we're talking about ionic compounds again. So each one is going to have a cation and an anion. And in order for the compounds to switch correctly, the cation of one compound is going to then become the cation of the other compound, and the same for the anions. So let's take a look at this a little more in depth. So here's an image of a double replacement reaction happening. Remember, the reactants are the things we start with, and so when you think about the reactants for double replacement reactions, generally both of the reactants are going to be aqueous, which is what we see here at the bottom. And then we're going to have to learn how to predict the phases of matter for the products, but that's what we're going to spend some time in this video doing. So starting out, we see we've got potassium iodide reacting with lead 2 nitrate. And we see potassiums as these blue spheres and the iodines as the purple spheres, our nitrate compounds and our lead atoms reacting together. And then when we take a look at our finished products, we're looking at the image over here on the right, we see now that we've got potassium with the nitrate, and we've got these lead iodide compounds all forming together. And so we see that the cations in this situation, the potassium and the lead, switch the anion that they're bonded to. So instead of potassium being bonded to iodine, it's now bonded to nitrate. And instead of the lead being bonded to nitrate, it's now bonded to iodine. So we switch what the cations are bonded to. So a little bit of a recap of what we just talked about. When we're thinking about the products of a double replacement reaction, you're going to switch the cations and balance the charges. So again, what this means by balance the charges, you are now writing the new formulas for the compounds produced by the reaction. One of the products has to be insoluble, and what that means is that it needs to be a solid or a liquid or a gas, but generally it's going to be a solid. And if both of the products that we produce through our double replacement reaction are soluble, what that means is that they are both aqueous, then we're going to predict that that reaction is not going to happen. And then similar to the single replacement reactions, if you predict it's not going to happen, you just write NR. So let's take a look at reading our solubility rules. And the solubility rules are over here on the right-hand side of the screen. I've provided a copy for you there. So looking at our first problem, we've got the example we were looking at on the slide before. We've got lead 2 nitrate reacting with potassium iodide. So when those cations switch, we know the lead, which has a charge of +2, is going to bond to the anion of the other compound. And in this case, that's going to be the iodine, which has a charge of -1. So when they crisscross, we get PbI2. And the potassium, do this in a different color, the potassium, which has a charge of +1, which was originally bonded to the iodine, is now going to bond to the nitrate, which has a charge of -1. So that final formula is going to be KNO3, which is what we see here as our predicted products. So that's the first step, is just writing out the formula for the products in your double replacement reaction. The next step is going to be using some reading skills. So you have to find the solubility rule that corresponds with each of the compounds. So let's take the lead iodide for our first example. So if you take a look at rule number 4 here, it says that all chloride, bromide, and iodide salts are soluble except for silver, lead 2 chloride, or lead 2, and mercury. So generally, if the compound had chlorine, bromine, and iodine, we would say that its state of matter is aqueous because it's soluble. But it tells us that lead is an exception to this rule. So if it's not going to be soluble, it's going to be insoluble, which is how we determined that its state of matter is going to be a solid. Let's look at the next one. So we have potassium nitrate. So first and foremost, we can look at rule 1 here. And rule 1 tells us that any compound from group 1, any alkali metal, is going to be soluble. So that could be one way for us to determine that this potassium nitrate is going to be aqueous. But rule number 3 also helps us here, because if we look at rule number 3 here, it says that all nitrate, chlorate, perchlorate, and acetate salts are going to be soluble with no exceptions. So that's how we understand that the potassium nitrate is aqueous. And since we have one product that is insoluble and one product that is soluble, we can predict that this reaction will occur. So looking at using the rules for the next one, we're going to just look at our sodium iodide and our potassium nitrate. So potassium nitrate's the same as what we've seen before. Looking at rules 1 and 3, we know that it's aqueous. And then when we look at rule number 1, again, sodium is an alkali metal, which makes this product also aqueous. And since both products can't be aqueous in a double replacement reaction, that's how we conclude that this reaction is not going to happen, and we write simply NR. So remember, solubility is simply how easily one substance is going to dissolve in another. Ionic compounds, as we learned in our writing and balancing video, are either going to be solids or aqueous depending on their solubility. When we use the word soluble, we're talking about aqueous substances. And when we use the word insoluble, we're talking about solids for our ionic compounds. So let's do the first one together again, and then you'll do the next 3 on your own. So we have to figure out whether or not the following compounds are going to be soluble or insoluble. So looking at sodium nitrate. So remember, sodium is Na plus, nitrate is NO3 minus. So that total formula is going to be NaNO3. So I look over at my solubility rules, and rule number 1 tells me that all elements in group 1, all alkali metals, are going to be soluble. So that means that this sodium nitrate is going to be soluble, aka aqueous. So I want you to go ahead and try silver chloride, cobalt 2 hydroxide, and iron 3 sulfate, and then check your answers. So now that we feel a little bit more comfortable with using the solubility rules, let's work on actually predicting our products. So when you're predicting your products, I want you to kind of think about it similar to foiling in algebra. The first and last ions of each compound are going to go together. So the silver is going to bond, which is the first ion in the first compound. It's going to bond to the last ion in the last compound. And then the nitrate is going to bond to the sodium. But remember, the cations are positively charged things. Always, always, always go first. So even though that nitrate looks like it would come before the sodium, since the sodium is the cation, that's why it ends up getting written first. So remember, cations always, always, always go first. And the same thing in the one below. So potassium, the first ion of the first compound, it's going to bond to the nitrate, which is the last ion in the last compound. And the barium is going to bond to the sulfate. So let's actually change this arrow here so that you can see the direction it's going to go. And that's how we end up with potassium nitrate and barium sulfate as our products. All right, so let's put it all together. So the first step when you're doing your double replacement reactions is always to predict the products. And this is where we're going to use that foiling idea. So here, the first ion of the first compound bonds to the last ion of the second compound. And remember, cations always come first, so that's why the hydrogen is going to come in front of the nitrate, and that's going to be nitric acid. and then the cation of the second compound bonds to the anion of the first compound. So we're going to get AgCl, because remember the charge on silver is always +1, charge on chlorine is -1, which is how we get silver chloride here. And so now we have to think about our phases of matter. So one way that we can remember this is we said that acids are always aqueous, but this is also supported by our solubility rules, because if you take a look at number 3, it says that nitrates are always going to be soluble, so this nitric acid is going to be aqueous. And then when we look at silver chloride, we're looking at rule number 4, where it says all chloride, bromide, and iodide salts are soluble except for those of silver, lead, and mercury. So since silver chloride is an exception to this rule, the silver chloride is going to be insoluble, which means it is going to be a solid. So once we've done the predicting the products and we figured out our phases, now we have to think about the balancing. So remember, when you're balancing a chemical reaction, you have to have the same type and same amount of atoms on both sides of your chemical equation. So if we start with hydrogen, we see that we have, I'm going to use orange here, 1 hydrogen in the reactant side and 1 hydrogen in the product side. So let's look at our next one, chlorine. We have 1 chlorine in the reactant side and 1 chlorine in the product side. So far so good. Let's look at silver. I'm going to switch up colors here just so we can see a little easier. We have 1 silver in the reactant side and 1 silver in the product side. And then since we see nitrate as a whole poly on both sides, we can balance it as one thing. So I have 1 nitrate in the reactants and 1 nitrate in the products. So this equation is actually balanced as it is. So let's try the next one together, and then I'll make you guys do the last one on your own. So the same steps are going to be used. So we start with taking and predicting the products first. So the first cation of the first compound bonds to the last cation of the other one. So we're going to end up with HOH. And what you're also going to see is that this is really H2O, because they're the same thing. Get rid of these markings over here. All right, so that's our first product. And now the cation of the second compound is going to bond to the anion of the first compound. So that is going to be Na2SO4. So now we need to think about our states of matter. So we go to our solubility rules. And if we start with water, we know that water is going to be a liquid. So we're going to give that a state of matter of a liquid. And now we're going to look at our sodium sulfate. So if we look at sodium sulfate, we see that sodium, because it's in group 1, we're looking at rule 1 up here, is always going to be soluble. So this is going to be aqueous. But remember, the only rule of when double replacement reactions isn't going to happen is when both of the products are aqueous. So since I have one product that's aqueous and one product that is a liquid, this reaction is still going to happen. So now we have to balance this equation. So let's start with looking at our, let's start with sulfate. So because we see sulfate as a polyatomic ion on the left-hand side of the equation and on the right-hand side of the equation, we can say that that is balanced. Let's look at sodium next. So here on the reactant side, I have 1 sodium, but on the product side, I have 2 sodiums. So I'm going to add a coefficient of 2 in front of that sodium hydroxide so that now my sodiums are balanced. And by adding that 2, I haven't changed anything about the sulfate balancing, so I'm still okay. Now let's take a look at hydrogen, or even hydroxide. So if you write water out like this one here, which is fine, it actually helps a little bit with balancing because we see hydroxide here as well as here. And so since there's now 2 hydroxides on the reactant side, I'm going to add a 2 here, which is going to help with my balancing of hydroxide on the product side. And then that 2 is also going to balance out the H2 from the sulfuric acid there. So when I rewrite this, just to make it a little bit neater for you guys to see it, we're going to end up with H2SO4 aqueous plus 2 NaOH aqueous to produce 2 water molecules plus Na2SO4 aqueous. So hopefully that helped with understanding how to predict the products, phases, and balance these equations. I want you to go ahead and try the last one where you're going to predict the products, phases, and balance potassium hydroxide and copper 2 sulfate. And then check your answers.